Welcome to this explainer, where we are going to dive straight into the absolute marvel that is the human heart. I mean, think about this for a second. Your heart beats around 100,000 times a day, every single day, and you literally never have to think about it. But how exactly does it pull that off? Well, today, we're exploring how the heart acts as its own completely self-sustaining battery. We're going to break down the microscopic electrical and chemical events that make just a single heartbeat possible.
Here is our game plan for today. We'll start with the heart's 4 superpowers, then look at automacy and the pacemaker, conduction and contraction, excitability and the action potential, the refractory shield, and finally, wrap up with adrenaline versus acetylcholine.
All right, let's jump right into Section 1, the heart's 4 superpowers.
So unlike your skeletal muscles, like your bicep, which just sits there waiting for a command from your brain, your cardiac muscle totally runs its own show. And it does this using 4 fundamental properties, or superpowers. First, we have automaticity, or chronotropy, which acts as the spark plug. Then there's conductivity, or dromotropy, which is the wiring system. Excitability, or bathmotropy, represents the tissue sensitivity to that spark. And finally, contractility, or inotropy, which is the raw mechanical horsepower, the actual physical squeeze of the engine.
When you lay out the formal textbook definitions side by side, you start to see this perfect self-sustaining sequence emerge. The heart spontaneously excites itself, transmits that electrical signal in a highly specific pattern, the local cells respond by depolarizing, and ultimately they physically contract. It's a beautifully choreographed dance.
Moving right along to Section 2, automacy, or the heart's pacemaker.
Now, what's truly mind-blowing about automacy is that the heart absolutely does not need your brain to tell it to beat. In fact, a heart removed from a body will actually just keep beating all on its own, as long as it has oxygen. That magic starts at the sinoatrial, or SA node. This little cluster of cells is our primary electrical generator. It's a natural pacemaker that just spontaneously fires at a resting pace of about 60 to 100 beats per minute. And from there, the excitation spreads out to trigger the rest of the cardiac muscle cells. So how does it do that? The secret is something called spontaneous diastolic depolarization. If you chart the electrical charge, it's never actually completely flat before a spike. Instead, there's this continuous, slow leak of calcium ions into the cell. It slowly raises the resting potential from negative 55 millivolts, just drifting upwards entirely on its own until it hits that negative 40 millivolt threshold. And then, boom, it inevitably fires.
That brings us to Section 3. Conductivity and contractility, the wiring and the squeeze.
To bridge the gap between that invisible electrical spark we just talked about and the actual physical pumping of blood, we rely on a specialized conducting system. The SA node sends its signal down specialized pathways to the AV node, down into the AV bundle, and finally out through the Purkinje fibers. And the coolest part is how this wiring wraps so precisely around the physical heart chambers. It guarantees a highly coordinated, unified contraction, pushing the blood exactly where it needs to go at exactly the right time.
Let's dive into Section 4, excitability and the action potential.
Once that electrical signal travels through the wiring, the local working muscle cells have to physically respond. Now, we aren't talking about the pacemaker anymore. We're talking about the dramatic electrical voltage shifts inside the working heart muscle cells that happen over just a few milliseconds. This is known as the action potential, and its unique 5-phase shape is the exact reason your heart actually works as a pump.
Let's walk through this narratively. Phase 0 is a massive, rapid upstroke. Fast sodium channels fly open and sodium just rushes into the cell. Phase 1 is a brief, tiny dip of early repolarization. But Phase 2? Phase 2 is the true game changer. It's the plateau. Here, L-type calcium channels open up slowly, and they stay open. This prolonged wave of calcium gives the muscle fighter the actual time it needs to perform a strong, sustained physical squeeze. After that, Phase 3 repolarizes the cell as potassium flows outward, and Phase 4 just restores everything back to the resting balance using cellular ion pumps.
Which naturally leads us to Section 5, the refractory shield. Because of that prolonged calcium plateau we just talked about, the heart naturally deploys an absolute biological safety mechanism. We call it the absolute refractory period. During this specific window of time, the heart muscle cell is completely deaf to any new electrical stimulation. It doesn't matter how strong the signal is, it's an unyielding shield. And why is this absolutely crucial? Because it guarantees that the heart muscle fully relaxes and has time to refill with blood. If it could be stimulated rapidly over and over again, it would go into a tetanic contraction. It would just violently cramp up and freeze. A cramped heart can't pump blood, which, as you can guess, would be instantly fatal.
And finally, Section 6, adrenaline versus acetylcholine, basically the gas pedal and the brakes. Okay, so we know how the engine runs completely on its own. But let's look at how our body uses external neurotransmitters to adapt to our daily needs. When you're in a fight-or-flight situation, your sympathetic nervous system dumps adrenaline. Adrenaline aggressively increases the rush of sodium and calcium ions, meaning that pacemaker potential hits its firing threshold way faster, jacking up your heart rate. But on the flip side, when it's time to rest and digest, the parasympathetic system releases acetylcholine. This acts like the brakes. It increases the outward flow of potassium, which drives the cell further away from the threshold, slowing the whole firing rate down. Mapping this out makes it super clear. The sympathetic adrenaline effect causes that slow depolarization to get much steeper. It tightly compresses the waves, so the action potentials just fire rapidly, back to back. Now contrast that with the parasympathetic acetylcholine effect. The electrical curve dips lower and stretches way out, taking its sweet time to finally reach the firing threshold, which slows your pulse right down. So, to wrap up all our biological vocabulary into one neat matrix, adrenaline basically throttles up the entire system. It creates a positive effect across the board. You get faster generation for positive chronotropy, faster conduction for positive dromotropy, higher excitability or positive bathmotropy, and a much stronger contraction, meaning positive inotropy. Acetylcholine is the exact opposite. It initiates negative effects across all these properties to calm the entire system down.
And that brings us to the end of our journey today. But it leaves us with a really fascinating biological question. If this whole system relies on such incredibly perfect, microscopic timing of sodium, potassium, and calcium, what happens when just one tiny ion channel misfires? Or what if it stays open literally a millisecond too long? Well, that right there is the root of deadly arrhythmias. Hopefully this explainer has sparked your curiosity to dive even deeper into the fragile, absolutely perfect mechanics of cardiovascular life. Thanks so much for learning with us today.